Alright, so I'm gonna be explaining another important article about domain adaptation. And like previous video, this time we're going to use this measure optimal transport to reduce this domain shift problem. The domain shift from source domain to target domain. So this paper in 2024 uses Gaussian mixture models, like previous video. And this paper is also very relevant to that. So we explored domain adaptation through optimal transport. We propose a novel approach where we model the data distribution through Gaussian mixture models. This strategy allows us to solve continuous optimal transport through an equivalent discrete problem. The optimal transport solution gives us a matching between source and target domain mixture components. From this matching, we can map data points between domains or transfer the labels from the source domain components toward the target domain. We experiment with two domain adaptation benchmarks in fault diagnosis, showing that our method have state-of-the-art performance. This is the Monge. Monge was a French mathematician working on optimal transport. So Monge formulated this optimal transport problem like this. And this one is called image distribution, or some people say push forward of T. Denotes the image distribution of P. Push forward of P by the map T, and C called the cost. What is the cost that we go from this distribution to another strange distribution? What is the cost of that? And for example, what is the probability of that? So multiplying by the probability of that. For example, for this point, if sample is here, if x is, for example, 0, then this has a higher probability. So the effort of transformation is even more important. So that has more higher cost. And an alternative description was proposed by Nye in terms of optimal transport plan, gamma. So gamma is an optimal transport plan. So we want to minimize this summation of all the costs, and instead of probability, we say multiply by d of gamma. Gamma is just your transport plan. And it's just a linear with respect to optimization variable gamma. So it is possible to define an optimal transport distance on P in terms of D. In terms of, instead of P probability, we use this plan. So the distance between P and Q, the Wasserstein distance between them is this. The approximation in this equation is at the core of discrete optimal transport. If you plug equation 4, this equation, if we plug it, this is the empirical approximation for P and Q because we don't have the real one. So the approximation is at the core. If we plug equation to equation 2, the optimal transport becomes computable. Now we can calculate this plan, the optimal plan. Where C is now more, we can understand it easily because it's just the cost between xi and xj, I drawn from probability P and j drawn from this probability. So we have a plug-in estimator. However, this estimator is susceptible to the curse of dimensionality. The convergence rate with respect to the number of samples is high, so the convergence speed decreases with data dimensionality. With equation 5, the notional map between P and Q is lost. We can recover a correspondence through the barycentric map. So x sub I is a good representation. So from x to x sub j for m different representations. And for the Gaussian case, when your probability distributions are just normal distributions with mean and variance, with covariance, then C of x, equation 2 then has a very close form, an affine form, which can be explicitly seen here. It has A and B, so our transform is very explicit. And even the Wasserstein distance is explicitly can be written like here. So the Gaussian case has advantages over the discrete case. For example, the estimation of parameters is not subject to the curse of dimensionality. Because Gaussian has finite, very small number of variables, and because of the shape of this normal distribution produces this explicit. So why do we care about curse of dimensionality anymore? A Gaussian mixture corresponds to P, where all of them are normal distributions. It's just linear combination of normal distribution. You have seen this several times, so we skip this. What is interesting in this paper, we describe domain adaptation for classification from the perspective of statistical learning. So we know the true risk, the real risk of a function, but we don't know the real risk, so we empirically approximate it. Because we don't know the real distribution, so we don't know the real risk, but we know how to formulate this empirical risk. So we explored domain adaptation, which corresponds to learning problem discretized by two domains. A source domain, where there will be data available, and a target domain, where we only have unlabeled data. So the gap risk under distribution P and Q can be measured by the distance between the probability. What is the Wasserstein distance between P and Q if you move from P to Q? The idea can be achieved through the barycentric map. So we propose new method through optimal transport between Gaussian mixtures. We have samples, and the first step is to learn a Gaussian mixture. Okay, after learning that, let's go and see. Once a component of target domain has been labeled, we propose domain adaptation. So we use a maximum posteriori principle to infer X. And here you see the visualization of domain adaptation when you go from source domain A to target domain C. So Gaussian mixture, these are proposed strategies for domain adaptation. And this picture is very interesting. You see, if in A, you see, we learn Gaussian mixtures from data from P and Q. Then in B, we compute the transport plan between these two probability distributions. And finally, in C, we visually show the plan. What is the cost of moving from these two to the other, where the dashed lines connect the components P sub I and Q sub I. Very interesting paper.